Welcome. In this video I'll introduce MHD shocks, and this is an extension of an earlier video, lecture 2 I think if it's labelled that way, where I looked at just fluid flow, so the Euler equations and what happens to shocks in gases. Now this will extend it a little bit to MHD cases, where it gets or can get a lot more complicated. So there's essentially it's applying conservation laws to nonlinear cases. So this is a very nonlinear situation where you have a discontinuity, a jump in the velocities or the densities and the pressures, and there are several different cases we'll consider. This first is a parallel shock, where you have a shock in the middle, so fluid flow coming in and then flowing out the other side, and in this case the magnetic field is perpendicular to the shock, and this turns out to be the same as the case in a neutral fluid, so that's the case of a gas. There's then a case where you have the magnetic fields parallel to the shock, and so the shock is moving the field into the shock. This is a bit more complicated, but essentially very straightforward. Then we'll look at cases where we have contact discontinuities. So this is not really a shock, but has a lot of the same properties. It can have jumps in the quantities, but there's no flow into the shock. It's just two fluids sitting next to each other, and then either flowing along the shock or not flowing at all. And these come in two different flavors: the contact discontinuity and tangential discontinuity. Again, kind of depending on where the magnetic field is pointing. The one case we won't cover is the most complicated, which is the oblique shocks. And this is where you have if this is the shock. So shock here, and then if you have the flow, say into the shock. If you have magnetic fields, which is at an angle to the shock, what does this do? So if you have B fields at an angle to the shock, then this can be very complicated. In general, MHD has three kind of waves. So there's the alpha wave, and then the fast and slow magnetic sonic wave. And so whereas the fluid flow, where we have Euler's equation, only has one kind of wave, the sound wave, now we have three. And so there are different kinds of shocks depending on what the flow speed is relative to these three different wave speeds. So this becomes more complicated, or there are more different regimes depending on the flow speed and the flow speed relative to these three different wave speeds. So that derivation is quite complicated, and so I won't cover it here, but this video will introduce the basic kind of shocks and discontinuities. Hopefully that will be a good start. So as I've drawn here, what we're considering is the case where we have a shock, and we're in the frame of the shock, so the shock is sitting still and the fluid is moving into the shock, and we have an upstream speed or velocity, an upstream density, and an upstream pressure, and then the flow is out of the shock this way, so we have U2, ρ2, and P2. So the fluid flow, density, and pressure out of the shock. You could think about this as being a shock moving into a fluid, which is probably what normally happens. So if you have an explosion, the shock wave moves outwards into the fluid, but we're moving into a frame where the shock is sitting still, and this enables us to look at steady state solutions, because you just have a constant flow into the shock and a constant flow out. What changes in MHD? So in MHD we have these three, as in a fluid of course, but we also have the magnetic field before and after the shock as well. So you need to add these extra terms in here, because we have more equations now to deal with. And so, like the fluid, we'll start with the conservation form of MHD. So you have the momentum, so the mass equation, so this is for the mass flow, which is the same as the fluid of course. This is the momentum. And I've highlighted the new bits in red here. These are the MHD parts, which are the bits that have changed. The rest is the same as the Euler equations. So this gives the momentum equation, so the momentum flow and the static pressure. And then we have the energy, which also has some extra terms from the magnetic field, where also the energy density E has some additional terms. So it has, as before, the kinetic energy, so half rho u squared, has the internal energy, which is just 1 over gamma minus 1 times the pressure, but now also has a term from the magnetic field, it's just the energy density of the magnetic field, b squared over 2 mu naught. So we have energy fluxes, so basically pointing flux from the magnetic field here in the electric field, and here we have an energy density of the magnetic field, we have the magnetic field pressure and tension, which is seen now in force balance. And so these terms modify the Rankine-Hugoniot equations across the shock. As before, the basic principle is that we're integrating these equations, assuming a steady state. So we're in a frame, rest frame of the shock. And so we're in steady state. And then all the terms, we're integrating these divergences across a very narrow layer across the shock, and then we're letting the thickness of that layer go to 0. And so the end result is that these terms here, the fluxes are constant, because this is the flux of mass, this is the flux of momentum, so this also constant, and as is this. So each of these three fluxes is constant across the shock. But then we now have, this gives us essentially three equations which are the slightly modified versions of the Rankine-Hugoniot ones for fluids. But then we need to also add other constraints. And so the other constraints come from essentially the Maxwell's equations. So we have source divergence of B is 0. But we also have an equation that we have D, so the induction equation. Once again, this component also needs to be integrated across the shock. These time derivatives, of course, go to 0. And so this part here, if x is the or say the horizontal direction is is perpendicular to the shock, this just says that the perpendicular component of B across the shock basically is constant, so that the flux of magnetic field, so if you integrate along the shock, for example, the flux of magnetic field into one side must be the same as out, and since the area is the same on both sides, the magnetic field strength must be the same, at least the perpendicular component must be. So if you have, say this is B perpendicular, it's this component which is at right angles to the shock. We can distinguish that from B parallel, which would be the component along the field, along the shock, sorry. So this is the component perpendicular to the shock, that must be constant across the shock. This one here we can just use essentially evaluate on both sides of the shock. Again, it's just saying this must be constant. And so this whole thing reduces the MHD Rankine-Hugoniot equations. So we have B perpendicular is constant across the shock, as I've written before. This term here just reduces to an equation for this is the perpendicular velocity, the parallel field on one side, and also we have the parallel flow and the perpendicular. So essentially evaluating this term here. This is also constant. So that comes from this equation, and here U parallel is the flow parallel to the shock. So here we have this is basically if I draw this on here. So we have U perpendicular, U parallel, and we have B parallel, which is the component parallel to the shock. And so in terms of these components, these components come from these Maxwell's equations, Ohm's law, goes from there. And then the other equations just write out again. So the mass gives us that rho times the U perpendicular to the shock is constant, because that's the flux into the shock and out of the shock. The momentum gives us several different components. So if you take the component perpendicular to the shock, so you have rho u perpendicular squared plus p. So this would be the total pressure in a fluid. But then now we have an extra component which depends on this. So if you take the diagonal, I'll show you where this comes from. So this is a tensor equation. So we have two indices. So here we take the perpendicular components of both. So we have u perpendicular squared. We take the perpendicular components of this, and just have a b squared, and take the perpendicular components of this, so there's a b perpendicular. And so b squared minus b perpendicular squared gives a b parallel squared, which is why there's a b parallel squared here. Then the other component we can take is the mixed component, so we have a u parallel, u perpendicular. So u parallel, u perpendicular. So u perpendicular, u parallel. And then because this is the mixed off-diagonal parts of the tensor, the p plus b squared term doesn't appear, and all that's left is the magnetic field tension term. So we have b perpendicular, b parallel, u naught. And this is also constant. So this is essentially the force balance in the parallel to the shock, and this is force balance perpendicular to the shock. And then finally the energy gives us an equation. Okay, so these are now the equations. So Rankine-Hugoniot equations for MHD shocks. So it's a bit more complicated than for a fluid, but the same basic principle applies. So we have these essentially 6 equations and 6 unknowns, whereas fluids only had 3 equations. And so we have essentially the downstream density, pressure, u parallel and u perpendicular, and also b parallel and b perpendicular. So if you know the upstream values of these 6 quantities, these 6 equations give us a solution for the downstream values. Okay, so now we can look at several different cases and reduce these to some simpler cases. So the general case where you have an oblique shock, so in general the velocity and the magnetic field might be at some angle to the shock. This can get very complicated. So we'll look at some simplifying cases. So first look at the parallel shock. And for reasons that will become clear shortly, this is something called the hydrodynamic shock. So this is where we have a shock like this. We have the flow basically into here, so at right angles to the shock, and we also have magnetic field B, which is into the shock, and there's right angles to it. So here we have B parallel is basically equal to 0, and to keep things simple, we'll also have U parallel equal to 0. Although that's not so difficult to deal with, because if there's not 0, then you move into a different frame and it becomes 0. So this is not the big one. The most restrictive is this B parallel is equal to 0. And you see that if you make B parallel equal 0, essentially this part disappears, because this is constant. This U parallel is also constant. Hence why you can change it just by shifting into a different frame. If this of course disappears with B parallel, and so that reduces to the same as the fluid case. Again here B parallel, this also goes to 0, and then this all is just constant. But lastly this part here, you have B parallel here, so this all disappears. So all the equations either become trivial or everything cancels out, and so it goes back to the same as the hydrodynamic case. So it's the same as the fluid case, i.e. if B equals 0. And so this is hydrodynamics, is the simplest case. And so again you have Mach number m1, so Mach number in the upstream must be bigger than 1, and the Mach number in the downstream must be less than 1. So it's slowing down from supersonic to subsonic relative to the sound speed. So shock is moves greater than the sound speed into the fluid. Okay, so the second case we'll look at is a perpendicular shock. This is where the magnetic field is parallel to the shock. It's like this, so you have B parallel. So B parallel 2, B parallel 1. And the flow is also U1, U2. So here we have that U parallel is equal to 0. I've set that B perpendicular equals 0. So one fairly straightforward result is if we look at this term over here. So if B perpendicular is 0, this term disappears, and all we're left with is this term here. So U perpendicular times B parallel must be constant. And this is analogous to this one. So here we have rho times U parallel. U perpendicular is constant. And so essentially the B parallel and rho work in the same way. So here, write down, so for example, rho U perpendicular is constant, implies that rho 2 over rho 1 is equal to U1 over U2. In the same way, we have, if B perpendicular is 0, we have that U perpendicular B parallel is equal to a constant. And so here this gives us that B2 over B1, these are both parallel components, is the same as U1 over U2, where these are both perpendicular. These are both U perpendicular, these are both B parallel. And so therefore, since these are both the same, we have that B2 over B1 is rho 2 over rho 1. And so the magnetic field is increased by the same ratio as the density. A bit more analysis will show that in this case the upstream velocity must be bigger than the sound speed plus well, it's basically the fast magnetic sonic speed. So we have U1 squared must be bigger than the sound speed squared plus the alpha in speed squared. So it must be faster than the fast magnetic sonic wave. And this makes sense in a way because the magnetic field acts as an additional pressure, so the pressure adds onto the thermal pressure, and so the wave across the magnetic field moves at the fast magnetic sonic wave, and so that's the speed at which pressure waves move across the magnetic field. And so to get a shock, you must have the fluid flow faster than this fast magnetic sonic wave. Okay, so those are the two simple cases of shocks in MHD fluids. So either parallel, in which case it's the same as either shock is parallel to the field, in which case it's the same as a neutral fluid, or it's perpendicular to the field, in which case you have a fast magnetic sonic wave. So the waves must be much faster. There's oblique shocks, which are much more complicated, and there the different families of waves become much more important. So the other thing I want to discuss are discontinuities, and these are essentially jumps which occur when there's no fluid flow across the jump. So this is where we have U perpendicular is equal to 0. So there's no flow across the discontinuity, but there's still a change in density and pressure and magnetic field across a narrow layer. And these can be important in several different regions. So can be important if you have two different fluids on top of each other or sitting next to each other. So for fluid boundaries, or particularly for boundary layers, so where you have a sudden change in magnetic geometry, for example, at the edge of the plasma, these kind of boundaries occur where there's a sudden jump or a sudden change in plasma parameters across a very narrow layer. Even though there's necessarily no flow across that discontinuity, it's still needs to be treated as a jump. So in this case, if we look at the equations, they also reduce to something much simpler. So if the perpendicular velocity is 0, then we have essentially a few things. So we still have this b perpendicular is constant. We just have u parallel b perpendicular is constant. So this goes to 0. Most of this disappears. So we still have some essentially u parallel, b perpendicular, u parallel here. So this part is also constant. And yes, there's some relationship here between the pressure. But most of these terms all vanish. So what's left is, so we have these four equations remaining for essentially the force balance in the across the discontinuity and parallel to discontinuity, and an equation for the energy as well. So there are several different cases here. So the first is a contact discontinuity, and this occurs where if b perpendicular basically is not equal to 0, so if there's some magnetic field across the jump, then you can see here is that essentially this, assuming that b parallel is also non-zero, so there's some non-zero magnetic field. If this is non-zero, then this is the same here. So this obviously here is the same as that. So this is constant, and this implies that also u parallel is constant. So if b perpendicular is non-zero, then b parallel is constant, and also u parallel is constant. And this is actually different from a fluid. So in a fluid, if you have two different fluids next to each other, there's essentially no limit to the change in velocity on, at least in equilibrium, from one side to the other. There might be stability limits, but essentially you can have two fluids next to each other flowing at different speeds. Whereas here, if there's magnetic fields across the jump, then the flow is essentially locked from one side to the other. So there's no change in flow across the jump. So the other case is a tangential discontinuity. And this is more usual for things like the edge of magnetic confinement devices, or where you have changes in magnetic field. So in this case, we have b perpendicular to the discontinuity is equal to 0. In this case, essentially these two equations disappear. They both go to 0. And so all we're left with are these two equations. So it's basically force balance perpendicular to the discontinuity, and this on the flux is also 0. So the only equation left is basically this force balance. And this means that this is what happens, say, at the edge, so the plasma vacuum boundary, for example, at the edge of tokamaks or other magnetic confinement devices. This is a tangential discontinuity, so that you have a radial force balance, but you can have arbitrary jumps in the other quantities. So you have jumps in all these quantities, subject to, of course, this one constraint. So if you're changing the pressure, then you have to change the B field so that this is constant. But essentially, there's no limit otherwise to things like the density. So density can have a jump at the boundary and still obey all these conservation laws.